Looking at 4.1, this is the first section of our study on polynomial functions. Also this semester we're going to study in great depth exponential logarithmic functions. So you saw that a little bit last year. That's usually the response I get. And then trigonometric functions, which a lot of students really like the unit on trigonometry, the stuff we do in trigonometry. We start this semester and go into next semester, and there's some closet trigonometry fans that come out of that. So you know you're a math geek when you like the trigonometry part, but it's new. There's some of it that's new and different, and it's very interesting, very practical, very applicable. As a matter of fact, I taught when I was at Cal Poly in the graduate program. Taught a quarter, a trigonometry class. We were able to do it just in a 10-week quarter class, which is about what we spend on it. Just trigonometry, and it was to forestry majors. So they had to take that, and there's just a lot of applications to it. So it's practical, so it makes it fun. Polynomial, don't be afraid of this here. Here's what a polynomial looks like. Okay, you've studied these already. Okay, so don't be afraid of them. The quadratics are polynomials, linear equations are polynomials. But a polynomial equation is one of this form right here. I'll let you write that down, and then we'll talk about what all those letters, it's like alphabet soup, and what all that means. So this polynomial is made up of the exponents, which are natural numbers. So the exponents here, that's an n, n minus 1, n minus 2, and then it goes all the way down to x to the first, and then a naught, and we'll talk about a naught in a minute. But the standard form of a polynomial is you write it so that the highest power term is first, like with our quadratic equations we've been looking at. Also, there are no variables under a radical here. So none of the variables are under a radical. Instead of writing the variables under a radical, you could write the variables to fractional powers. We studied that part last year too, and that's equivalent. So this is kind of redundant here, but it's helping you to understand what the form that they look like. But exponents are natural numbers, so like 0, 1, 2, 3. As opposed to 1/3. To have a power like 1/3 on a variable would be equivalent to having cubed root of x, and so we're kind of saying the same thing with these. The coefficients are the a sub n minus 1, all the way to a sub 1. We call those the coefficients of the variable in the polynomial. And the last term on there, a naught, is called the constant. And then the degree of the polynomial is the highest power. It's usually, if you've written it in standard form, you can see it right away with the first term. So quadratic would be of degree 2. A linear expression, yeah.
What is the
Constant is a naught. We call this a naught, or a sub 0. A naught. It's just the number that does not have a variable attached to it. So if you think back to your parent graphs, do you remember if it's squared or to the fourth? I think you have each of those on your parent graphs. What's true about the squared and fourth degree polynomials in terms of their end points as it goes to the right or to the left? Can you draw? Yeah. They go in the same direction, so you might want to just make note of that. But I think you've memorized those. So they go in the same direction, either both up or both down. If there's a negative out in front, it's going to flip it over. And then the odd ones, third and fifth, are in your parent graph sheet. and those go in opposite directions. So even versus odd. Should talk about multiplicity as well. It's how many times a factor exists. And I have some examples on Geometry Sketchpad to show you, or an example of multiplicity, show you what I mean. It's how many times a factor exists. So if you have something like a quadratic that's a perfect square, like x minus 2 squared, that means we have a factor of x minus 2 with an even multiplicity or a multiplicity of 2. And so that's going to mean it's just going to, the parabola just touch the x-axis. You've seen that before, but we're going to apply that then to higher degree polynomials. If this m here is short for multiplicity, if the multiplicity is odd, that means the factor only shows up 1, 3, 5, 7 times, an odd number of times, then the graph crosses through the x-axis. And if the multiplicity is even, so if that particular factor shows up 2 times, 4 times, 6 times, it just touches the x-axis at that particular 0. Because remember, if x minus 2 is a factor, what is the 0 of that polynomial? 2 is, yeah. So what we're saying is that if x minus 2 squared was a factor, then the graph is just going to glance off of the x-axis at x equals 2. That's all that that's saying. Here's my example of that. I'm going to have to go to my computer here. I have a Geometry Sketchpad. Here it is. This is actually the wrong page. Multiplicity. So here you can see, and you could write this down as an example, but here you can see a polynomial. By the way, what's the degree of this polynomial? Can you figure it out? Looks like, yeah, it's a good guess, the second, because we have the second power, but what about this x here and this x here? What's that going to do to the degree? It's going to make it actually 4th degree. If you were to multiply this all out and write it in standard form, the highest power would be an x to the 4th right in the beginning. So this is one of the factors. What is the multiplicity of this factor x minus 2? Is it odd or even? The power on this factor is 1. So since 1 is an odd number, this has a multiplicity of that is odd. So that means if you find the 0 that goes with the x minus 2, it's right over here. See the arrow here? I can't make it. So right over here, at x equals 2, notice that the graph of the polynomial function goes through x equals 2. X plus 1 squared has a multiplicity of 2. That is an even multiplicity, meaning that at the 0 associated with this factor, x equals negative 1, which is right here, the graph just touches the x-axis, glances off of it. And then x plus 4 has a multiplicity that is odd, so at x equals negative 4, it goes through that 0. So that's what we mean by that. Does that make sense? Okay. So going back over here. Number of local extrema. This is a typical section 1 of a chapter in a math book. We got a bunch of definitions. The local extrema, if the degree equals n, then the max number of extrema is n minus 1. I put this all in caps. It doesn't mean that you will have n minus 1 extrema. It means that the max number would be n minus 1. So if the degree is 3, you could have up to 2 mins and maxes. Think about a quadratic. The degree of a quadratic is 2. How many maxes or mins do you have in a quadratic? Just 1. So 2 minus 1 is 1. Now, with the cubic, I'll show you my sketch pad here. Extreme in here. Okay. With the cubic, or actually this is a quartic, so 4th degree. With a 4th degree, what I claim there is you could have a maximum number of extrema that is 4 minus 1 or 3. Look at the blue graph here. How many extrema do I have on the blue graph? It looks like 1. Yeah, that was a good way to put it because you don't know if I have the whole graph here. Everything you need to see is here for the blue graph. So you're right. there is only one. So that's what it means. The max number would be 3. In this case, there's only one. Okay? And so it depends on what the coefficients are here and stuff, what the whole polynomial looks like. In this case, it's just the parent graph. There's only one. But on this one over here, this is a 4th degree polynomial. It looks like a mess, but it's 4th degree. And it has 1, 2, 3 extrema. And extrema is plural for maxes and mins all together. Okay? So if you know the degree is 5, there could be up to 4 maxes and mins. All right. One more thing here, in behavior model. As the absolute value of x gets large, the polynomial resembles the graph of the highest term. Very calculus sort of idea. It says as absolute value of x approaches, say, infinity, as it gets large, so it's getting closer to infinity, or even if it goes towards negative infinity, the polynomial is going to resemble whatever the highest term is. So it'll look like an, if it's a cubic polynomial, that's what it'll look like on the endpoints. Is it'll start to look like that steep branch heading up towards infinity. Or as you go to the left, that steep branch heading down towards negative infinity. If it's a quartic, a 4th degree, then it's going to, as you go towards infinity or negative infinity, it's just going to have a branch just going up in the same direction. So what it's saying is that when the value x that you're plugging in is really big, the terms that follow after the x to the 4th have very insignificant effects on the graph of it. It's looking like whatever that leading coefficient is. That's the idea behind the end behavior model. Let me show you a picture of that as well. So on the geometry sketchpad here, this is a cubic polynomial. It's x cubed minus 5x squared minus 2. This looks like your parent graph for x cubed. That's what's happening. This x squared and minus 2, especially as x gets really large, doesn't matter. But what these terms in here do is shift it and then kind of stretch it as well. But you know, as x goes to infinity, this graph is really just looks like x cubed. And so what's nice about that is that you can take a simpler function and use it as the mathematical model for a more complicated one with lots of terms as x gets really large. Okay, and that's also an idea in kind of a calculus idea. Is the idea in calculus we actually go the other direction. If you're looking at a very small interval on any curve, you can actually model that small interval with a line. Just think about it, right? I mean, this is what your graphing calculator is doing this. It's taking a whole bunch of little short line segments to make up the curve. So in a small interval, it's really just linear. And is there any easier function than a linear function to analyze? I don't know, right? That's what you started with in algebra 1. They're the easiest ones to analyze. So on a small interval, they're linear. This is kind of going on a bigger scale. This is saying as x approaches infinity or negative infinity, it looks like x cubed. So you could just use y equals x cubed and plug in values to that if it's going to be a real big value of x or a real small negative value. Right. And there are advantages to that. It just kind of helps us to come up with a simpler model, which is easier to analyze. All right. So what we're going to be asked to do is, given, say, examples of polynomial functions, to try and decide things like what degree is it. So let's look at number 1 here. So you have a picture of number 1. Usually what I end up doing is looking at which way the arrows go. So is this going to be even or odd, looking at the arrows here? Oh. Yes, it's odd. How do you know it's odd? Arrows are going opposite directions, so it's odd. Good. What about the second one when we look down here? Arrows are going same directions. It's going to be even. Okay. Smallest possible degree. Smallest possible degree. How do we figure that out? Well, that's where we start counting humps here. So there's 1, 2, 3, 4 humps. So the smallest possible degree of this guy is 5. It could be of higher degree, but the smallest possible degree is 5. It's working backwards from what I said up here. We're counting the number of extrema. That's the n minus 1 part, so if I add 1 to it, that's the smallest possible degree. What about here? What's the smallest possible degree? Well, I count humps. It's 1, 2, 3, and then I add 1 to that. Smallest possible degree is 4. Now, this goes back to your parent graph again. Leading coefficient, is it positive or negative? Well, you have to think about your parent graph for the cubic. The parent graph for the cubic, can you draw it in the air? What does it look like? It wiggles it goes like this, right? So has this, based on the parent graph, been flipped, reflected over the edge? No. So what does that tell you about the coefficient of the leading term? It's positive, yes. Whereas on this one down here, it typically faces up on the parent graph, so the coefficient must be negative. You with me? All of this can be related to the cubic and the quadratic, second degree and third degree, because the second degree gives us the pattern for fourth, sixth, eighth, and so on. And the third degree gives us the pattern for fifth, seventh, ninth, and so on. Okay. So a lot of what we study is just third and fourth degree, and then those principles apply. Real zeros, you can see them right here on the graph. There's one at negative 3 right here, and one at negative 1. Down here on the second one, my real zeros are at negative 1, 1, and 3. You can read it right off the graph, or 4 it looks like, sorry. 1, 2, 3, 4. So you can read it right off the graph where the zeros are. The zeros are where the graph touches or crosses through the x-axis. Now in terms of multiplicity of the zeros, the multiplicity up here of negative 3 is odd. How do I know that based on my definition? It crosses through the x-axis, whereas negative 1 is even because it merely touches. And the same thing over here. We can talk about multiplicity of our first 0, negative 1, as odd because it crosses through. The multiplicity of 1 is even because it touches, and the multiplicity of 4 is odd, it crosses through. All right, I'm going to give you a chance to try some of these in the last 15 minutes of class, so you get to try some of these. You may even make your way through most of the assignment. It'll be helpful just to try doing this on your own, but I want to give you the information first. All right. It says for each polynomial, and we're given one right here. This is the polynomial down here. It's already in factored form just to make life easier. We're going to talk about factoring once we talk about the rational root theorem, which it sounds like you heard last year, but we'll look at that in some more detail. It says for each polynomial, list the real zeros with multiplicity. Determine if the graph crosses or touches at each. Determine the max number of extrema, and then sketch it. So we can kind of talk about all this in the context of sketching it. So let's go ahead and do that. What are the real zeros? Can you tell me what they are just by looking at this? Negative 4 is one, yeah. So we can go over here at negative 4 and place a dot. And also at negative 3, okay, and place a dot here. Okay, so we got that. List the zeros, well, we're going to draw them on the graph. Okay? We can list them too. They are negative 4 and they are negative 3. And then we'll do like we did up above. What is the multiplicity of each of these? Well, this one is odd or even. Looking up here, what do we do up here? It says multiplicity of the zeros is the green here. We're listing odd or even. So when it asks for multiplicity, we're listing odd or even. So going back here, is this an odd or even multiplicity? Odd. And then the other one is also odd. Okay. So then determine if the graph crosses or touches at each. So if it's odd, it's going to cross. So it's going to cross through at each of those. And then determine the max number of extrema, the number of turning points. So what degree is this? Yeah, it's 3 plus 1. So the degree is equal to 3 plus 1, or 4. And so determine the max number of extrema. Is 4 minus 1, or 3. So max number of extremas. So this is going to be a really rough sketch. We know where it crosses through. The other thing we know is it's positive, so down here it's going down over here, right? And then up over here. So what could the graph look like? So it's going to cross through. Max number of extremas is 3. There are kind of a lot of different options. Do you have any ideas? Maybe think about it. Why don't you, in pencil, see if you could sketch it, then we're going to graph it on the graph detector and see what it really looks like. When we say sketch on these, here's all we care about. Here's all we care about for now. The zeros, whether it crosses through or just touches, that'll make a difference as we move to calculus. And then the direction as x goes to infinity or negative infinity, that's all we care about. So you could have lots of different options on here. Remember, it's max number of extrema is 3. If you drew something like, if you're thinking in your mind something like this, there's nothing wrong with that. Max number is 3. It doesn't say there has to be 3. Do we really know without thinking a little more about it? No, not. I know two things I know to be true. It goes through here and here, and it looks like that as it goes to infinity. Otherwise, I don't know. So, you might. How many of you are thinking of that? Okay. Let's see what happens. Let's see. Could there be another wiggle somewhere in there? We just don't see it? Yes, it could be. We saw that in our sketch pad. Let's see what it looks like. So you're going to graph x plus 4 times x plus 3 cubed. So y equals, and I would encourage you just to type it in just in that factored form as I did there. So x plus, forgot already, it was x plus 4, and then x plus 3 squared.
Cubed.
Oh, cubed, yeah. Cubed. There it is, x plus 4, x plus 3 cubed. Because we've changed around our windows a lot, you might want to hit zoom after you type that in. And then z standard number 6. Let's see what it ends up looking like. No, different way. So you see that wiggle in there? If I zoom in a little bit, it looks different than what we had in our minds, which is the way it goes. But you'll zoom in there. I just zoomed in at the wrong spot. I zoomed in at the origin. Okay, so let's zoom out. So you can do a zoom out. When you hit zoom, you got to hit number 2 or 3 and then hit enter to actually get it to do the zoom. But you can see in there, you can kind of see it goes through and then it has a little wiggle in between. So it ends up looking a little different than what we thought. It has that little wiggle in there. But on the ends, it looks just as we suspected. So it comes down, let's see, I don't think we're seeing the whole thing. I have to zoom out more. All we're seeing is a part of it. We know, let's see, third, oh, you said it was 4th degree, sorry. I scared you wrong on that. That's why, it's good to go. It's 4th degree, so actually it does not come down over here, sorry. It comes down here, has a little wiggle in here. Graph. So it comes down, wiggle, and then heads back up. So, I was thinking odd power overall. Incorrect. Has a little wiggle in here and then takes off, and then so it does go in the same direction because it's 4th degree, not 3rd degree. It's only 3rd degree. There's the graph of it. But all we care about is really the endpoints, where it crosses through. I mean, those are so the end behavior models and the zeros. All right, what about this one down here? Let's see if we can go through the same process. What are the zeros? Yeah, so we have 5 and negative 4. What's the multiplicity of 5? odd. This one's even. So this one's going to cross. This one's going to touch. And then the max extrema. Max extrema, well, we have a degree of 5, so the max extrema would be 4. So this one really is odd. This one's odd, so it's going to look good. And then we have this coefficient out in front, the 2. It's not negative, so it won't flip it over. So at 5, we have it crossing through. And at negative 4, it just touches. And this time, we do know that from here it goes down like this, and from here it's going to go up like that. And then in between, we don't really know what happens. So if we graph it, some of you already graph it on your graphing calculator. 2 times x minus 5 cubed, x plus 4 squared. I mean, our only other option would be to do some calculus or do some plotting of points. But let's see what it looks like here. Right, it was 2. And then the first one was x minus 5 to what power? The third, okay. And then the next one was to the second. Graph here. You know what's happening over here? It gets so vertical that it's not handling it very well. Let's see if I back it up a little bit. I think it's frozen. Well, it's frozen. We'll do that one. So the max number of extrema before this thing is odd. So we have, it just touches right here. Let's see, we could have lots of different options for graphs. Let's see, it could have 1, 2, 3, 4. That could be one option. Exactly what it looks like, but there it is. All right, what about this last one on here? We have a negative x, a 2x plus 1 is a factor, and x minus 3 is a factor. So what are my zeros? What 0 goes with this first factor? 0. What about with this one? Can you do it in your head? Negative 1/2. And then here we have 3. And so this one is odd, odd, even. So odd, odd, even. So at 0, does it go through? So it does. We're going to cross here. Cross. And touch. So we got it going through at 0. And we've got it negative 1/2, it crosses through. And we've got it touching at 3. And what are the max number of extrema here? First of all, what's our degree? We have 2 plus 1 plus 1, so the degree is 4. So max extrema would be 3, and it's even, so in the end they're going to go in the same direction. Which direction are they going to go based on this coefficient out here? Is it negative? They're going to both go down. So in the end here, down and down. And it just touches. It's going to just touch at 3, right? Just touch at 3. Okay, so that means it has to bounce off of there. Let's see here. 1, 2, 3. No, that's too many of them. That's not going to work. Negative 1/2. Down. Through. There's one extra wiggle in there. It's not going to work. that's a possibility there. Is there 1, 2, 3 extrema? So maybe that's a possibility. It does. It has to go through -1/2 and then through 0. So it's got to actually go through. So up, above, and below. So it's got to go through the -1/2 and then through 0. And it's just kind of the process you take when you're sketching it. Yes?
So are you trying to put like a label on the are you saving it for the 4 through the 1?
Uh-huh.
Okay, that was always the
One last thing, yeah. And it's up to that many. There could only be, there could only be 2 wiggles. I mean, this is very kind of, you're just a very rough sketch, and so we don't know. But what we do know is the end behavior model we know, and we do know the zeros, what they are. Okay, and that's about it. And those are the key points or critical portions of the graph we need to know. The reality is we have technology. We can graph it. It's not hard. Okay. Going the other direction is really easy, so these last 3 will be simple here. You've done this before with quadratic, but it says find a polynomial, so any polynomial of degree 3 whose zeros are -3, 2, and 5. So if I wanted to find a polynomial, let's call it f of x, and these are the zeros, then the factors would be x plus 3, x minus 2, and what's the third factor going to be? X minus 5. Right. So we're building polynomials from 0. And so my polynomial, this is it. I could stop here if I wanted to. That's it. Okay. If I'm asked to write the polynomial in standard form, which they will ask you in some of them, then I have to go ahead and multiply it out. So let's just do that on this one. The rest of them we're going to leave just in factored form, unless we're asked to do otherwise. So here we have x squared minus 2x plus 3x minus 6. We're going to simplify that, then multiply it by x minus 5. Oops, that's not going to work. So right here I have x squared plus x minus 6 times x minus 5. And that's going to give me, by distributive property, x to the third minus 5x squared plus x squared minus 5x minus 6x plus 30. And then we're going to combine the like terms here. So my final answer is f of x equals x cubed minus 4x squared minus 11x plus 30. If you're asked to multiply it out, I wouldn't even mess with it unless you're asked to do so. And leave it in factored form. We're going to do that on this next one. So find a polynomial such that -2 is a solution with multiplicity of 2. What does that mean? Let's call this p of x. -2 is a solution with multiplicity of 2. So that means x plus 2 is a factor, and it's squared. So it's an even multiplicity, and they're telling us even how many times it shows up. So x plus 2 squared. And 4 is a solution with a multiplicity of 1. That would mean x minus 4 is a factor. And so there's my polynomial. Like that. Okay, that's when I say there's my polynomial, I mean there's one possible polynomial. There's an infinite number of them because I could put different terms out here. It doesn't even, I mean, I could be a negative out here, -1, a -2, any coefficient out here. So there's one possibility. And then this one, how about w of x? Find a polynomial of degree 4 with zeros of 1, 2, and -2. Oh, okay. So this would be a choose your own adventure. Because I only have 3 zeros, that means one of the zeros has to have a multiplicity that's even, that's 2. So which one do you want to pick? Let's just write them down here. So we have x minus 1 is a factor, x minus 2 is a factor, and x plus 2, and one of them has to be squared. So we could just pick any one of them. We could all have something different. So there it is. There's one possible polynomial with a degree of 4. 1, 2, 3, 4, and these are the zeros. And they're not telling us which one has a multiplicity of that's even, that's 2. So that's it.